In the previous lecture, we discussed the quantization of conductance in ballistic constructions or ballistic one-dimensional conductor. In this lecture, we will look into the mechanism or the physics or the mathematics of how under what conditions and what are the details of this quantized conductance through the system. Okay. So we will discuss the mathematical formalism, which is called the Landover-Whittaker formalism. We'll look into how to get the current from the transmission, and eventually the quantization of conductance in these systems. And we also will discuss a close connection between the quantization of conductance in the constriction and also that of the quantum Hall effect that we discussed in the previous module, one of the previous modules. Okay. Now, the Landover formalism or Landover-Whittaker formalism considers the system as something like a black box with certain transmission coefficient Tk, which is decided by the scattering in that region in the box. So you have something like a scattering center and with a transmission probability or transmission coefficient Tk, and you have applied a small bias EV across the system, where mu L is the electrochemical potential on the left side and mu R on the right side, and UL and UR are the band edges, conduction band edges on the source and the drain side. And the transport is going from left to right, but you also have right to left transport too. Okay, the predominant transport in this case will be from left to right, but you need to consider both transport in both directions for a complete picture. Okay, so let's write down the expression for current. Okay, in this case from left electrode to right electrode, what you have is IL into 2E. That 2 stands for the spin degeneracy. E is the electronic charge, which multiplies this particle current into the electrical current. The integral here has few terms inside, but dk by 2 pi tells you how many number of states are there. 1 by 2 pi is your number density. Okay, in this dk window, how many states are there? Vk is the group velocity for the state k. Tk is the transmission for the state k, transmission coefficient for the state k, and F is the Fermi function for the left electrode. So what is the occupation of the state? What is the number density? How many states are there in the channel, and what velocity these states move, and what is the transmission coefficient for these states? So it is integrated over all the positive values of k, because it's a one-dimensional transport and we are considering from left to the right. Okay, when you consider right left, you have to consider all the negative values, or you put a negative sign. Okay, that's what this formalism is. Now, so far what we have discussed is in the k space, but energy space is what we always work. because voltage is a scaled form of energy. If you multiply voltage electrical charge, electronic charge, then you will get energy. So energy is what we actually we vary in the transport. Okay. So the dk integral over dk, we need to convert an integral over dE, energy. Okay. So dk by d into dE, but dk by dE is basically 1 by h bar into v. V is the group velocity by this formula. Okay, h bar divided by dE by dk is the group velocity. So let's substitute that here. So dk is 1 by h bar v into dE. So this expression for the current from left to right, eventually you will get 2e by h integral UL in infinity, where UL is the conduction band, okay, bottom, because that is where the energy starts from, okay. Because you don't need to consider the whole 0 to infinity here, because the energy available, starting energy is UL to infinity. When you consider this side, it will be UR to infinity, okay. UL to infinity, then Roomy function, then transmission probability for the state, then energy E, integral over dE. That's what you're going to get. This is the current from left to right. But there is a very interesting situation here, which happens only in this one-dimensional situation. Because you had a term here in the case space, a group velocity term, and you also have a term which says what is the number density. Okay, you had two terms there. Okay, or the density of states. Both of them actually disappeared now when you took the integral, when you rewrote the integral in the energy space. Because the group velocity vanished from the expression for current or conductance. That's what happened. That the reason is the one-dimensional density of states and the group velocity. In 1D, the density of states and the group velocity cancel each other. Because group velocity V and density of state also has a and this the integral over E actually has a Newton. I mean, that is the density of states. Okay, it also has a beta, that is the density of state. So you can conceptually, what you can think is the states at higher energy moves faster because velocity is proportional to the square root of energy. Okay, because we are considering these are free particles, free electrons. Of course, they are confined also, but the wave is a plane wave. Okay, so the velocity is proportional to square root of E, and density of states is proportional to 1 by square root of E, because dE by dk is going to give you 1 by square root of E. Okay, so that is the cancellation happening here. The velocity of state and the density of state are kind of inversely proportional. So what you can say that, but still the expression is same, because when you have higher velocity, the states move faster, but there are less number of states. At lower velocity, there are more number of states, so both of them carry the same number of electrons, or the current would be same. We have more states but less velocity. You have higher velocity states, but they are less in number. Okay, so these two terms effectively cancel each other, so that the eventual expression for current will not have a velocity dependence and also density of state dependence. That's what we are seeing here. All the states carry the similar same current. I mean, contributes similar. That is what we are seeing. So similarly, the current from right to left is the integral over UR to infinity. Similar format, but you can see a negative sign because those are left propagating states. Okay, current from right to left and current from left to right. So that's what we have now. These are the expressions for the two contributions to the current. Now the total current is the sum of these two terms, and the integral for the left to right starts from UL and right to left starts from UR. But remember, if you look at this energy diagram across the device, this states, okay, in this energy window doesn't contribute anything because there are no corresponding states available here. Okay, so you don't need to worry about integrating the right hand side in this range UR. You can start integral for the right hand side also from UL because there are no states here to propagate. Okay, there is nothing. It's a forbidden region. Okay, because that's a band gap. So you don't, that is the bottom of the conduction band. UL is the bottom of the conduction band. Below that, you don't need to worry. What that means is that gives us a convenience that these two integrals can be set from UL to infinity. And that's what we have. So the total current is 2E by H, UL to infinity. Then also one more assumption we have made is the transmission coefficient is direction independent. So TE is same whether you are going from right to left or left to right. Okay. So when you factor all this in, the whole expression becomes 2E by H integral UL through infinity, and the difference of the Fermi functions f of E mu L and f of E mu R, then the transmission coefficient integrated over energy from UL to infinity. Okay, but as you can see, this is not something like V, I is equal to V by R format. And this is not Ohm's law. Okay. All we can say is I is equal to 0 when V is equal to 0. Because when V is equal to 0, mu L is equal to mu R. And this difference of these two Fermi function will go to 0. So the whole integral will be 0. So that's the only thing we can say. But definitely, this is not going to give you, this is not Ohm's law. This is not in the form where you can directly get Ohm's law from this. Okay. The transport is actually different when you treat this way. Okay. Now, let us now look at the transport from this framework for different regimes, okay, for different cases. The first case is where you have very large bias, really large bias. So when you have very large bias, you don't really need to worry about the states which actually propagating to the left side from the right side, because when you have large bias, you can say that there are no states here on the left side which are ready to receive the electrons coming from the right side. Okay. What that means is, because there are two reasons. Number one, there are no states here. Secondly, most of the states are actually full, because this is the bottom of the conduction band and the filling starts at the bottom. So the bottom side of the conduction belt is already full. So there are no vacant states here to receive the electrons from this side. So what I'm saying here is you can ignore the contribution from the right side and you can say the total current is only that which goes to the left. I equal to IL. IL is the current which is going to the left. That is fine. Okay. Now when you have small bias, okay, then the Fermi function can be expanded to the lowest order. This difference in the Fermi function you can write as EV into dF by d mu, okay, which is minus EV into dF E mu by dE, okay, when you convert this mu into the voltage scale, in the energy scale, okay. So then you'll accumulate this minus sign, okay. Now the current is 2E square V by H, okay, because you have 2E from here, from the original expression you have 2E, then you have E, another E coming from here, okay. So what you're going to have is 2E square V by H into integral UL over infinity dF by dE mu by dE, that comes from here, okay, and T is the transmission probability, okay, or transmittivity. Then the whole integral runs from UL to infinity dE, okay. Now what you can say is in this limit the current I is proportional to V. Rest of things are independent of V, so I is proportional to V, okay. That is Ohm's law. So in really small bias range where you can expand the Fermi function like this, in that limit the Ohm's law is going to hold in this situation, okay, because the conduction in that regime is proportional to the applied voltage, because the rest of the things are actually independent of voltage, okay. So in that limit Ohm's law is going to hold. And the conductance G is given by this 2E square by H term and with a dimensionless quantity. This thing is dimensionless because 2E square by H has the dimension of conductance and this integral is dimensionless, okay. Now this E square by H is the quantum limit of conductance, and 2 here, as we mentioned in the beginning, it represents the spin degeneracy because there are 2 spin channels, okay. Now let's consider the next case where the system is at low temperature, okay, or what is the low temperature transport look like? How does the low temperature transport look like? Now in the low temperature you don't have the Fermi distribution. In this previous case you have something like a Fermi distribution you can consider on the lead, but that is what I have tried here to represent by changing the color. Now here it is a step function, it's a clear step function, okay. at low temperature. There is not much broadening. Okay. What that means is there are all the states until mu L is full, or there are no states on the left side vacant because it's a step function, and all the states below mu L is full. They are not ready to receive any electrons on the right side. All the states above mu L is empty. Similar case for the right electrode also. What that means is you need to consider only the current which is contributed in this window, only from here, the electron going from here to here. That means I is to E by h bar mu R to mu L dE into dE. Okay, because the Fermi function is 1 in that region because it's full, or 0 for other side, or other direction. So you need to consider only the transmission probability or transmission coefficient for those states through the channel or through the system. So the current is simply given by the transmission coefficient of the states in the system between mu R and mu L. Now, at very low temperature and very low energy window, because at low temperature the Fermi function is very sharp, okay, and compared to any other feature, okay. So the states are there available only in a very thin window, okay. So dF by dE, the derivative Fermi function, is a step function because Fermi function is the sharp step. Sharp, it's a very clear sharp step function. So the derivative will be a delta function, delta of E minus mu. Okay. What that means is transport is going to take place only at the Fermi surface. Substituting this in this equation, which is what we have derived here, okay, you get 2e square by h bar UL in infinity, this function, but this function is now a delta function which has value only at mu. So this is going to reduce to 2e by t mu, but t mu is the transmission coefficient for that particular, or transmission coefficient at mu, okay. And for ballistic transport, as we have seen for the quantum point contact or atomic point contact, each of these channels are reflectionless. There are no scattering inside the channel or inside a device. That means the transmission coefficient is 1 for every channel. Every channel is fully transmitting. There is no reflection from that channel. What that means is all the channels got the same conductance, because conductance depends only on the transmission. It does not depend on the dimension of any other parameter. It doesn't look at how long the channel, how wide the channel, nothing. It actually looks at what is the transmission coefficient for the channel and how many channels are there. This is the total transmission coefficient for the device and multiplied by the conductance quantum, okay, and 2 is for the spin degeneracy here, okay. Now in this context, let us revisit the quantum point contact and also see how does that compare with the quantum Hall effect, because there also you have conductance quantization, here also you have conductance quantization. Here you have conductance quantization as a function of magnetic field, here you got that as a gate voltage, okay, and they both give you the same quantization, but how they are related. Okay. Now that's what we are going to address. Now you have the formula for conductance here, which is 2e square by h into the transmission coefficient. Again, we are considering the transport at very low temperature, okay, in the ballistic reflectionless regime, where T is equal to 1 for every channel. And there are no mixing between the channel. You also have to consider that part here. I want to mention that these channels are, in this case, these are the eigenstates for the harmonic oscillator potential, parabolic potential. They are Hermitian. In this case, again, they are the eigenstates for harmonic oscillator potential. Here also we have considered they are parabolic potential or simple harmonic motion. Okay. What that means? There are no mixing. That means every channel it goes through and it doesn't reflect or it doesn't scatter to another channel. Okay. Yes, there is a streamlined flow of electron through each of these channels. Okay. And transmission is 1 for each of the channels. So now, when we vary gate voltage, you are reducing the number of channels, or you are changing the number of channels one by one, and you get a step in the conductance 2e square by h. And if you have done this with the magnetic field, you will get E square by h. Okay, so the conductivity Eg is E square by h into n, where n is the number of channels. Here, this is a representative plot for quantum Hall effect, where you are plotting the Rx, the Hall resistance rho xy, which is also showing similar behavior, a step-like behavior in h by e square. If you plot conductance, you will get something similar to this in this case. But here, this is a plot of the resistance, resistivity, or rho xy. But here, every step is quantized. The resistance is quantized as h by e square into 1 by n, or the conductance is quantized e square by h into n. If you just invert this, you will get this. Okay. So here what happens is, when you vary the field, you are reducing the number of edge states one by one, but these edge states are perfect one-dimensional channels. They are actually a lot more perfect one-dimensional channels than the one-dimensional channels given by the quantum point contact. The reason is, in quantum Hall effect, you don't have any backscattering, because backscattering is forbidden, even though you have minor impurities or defects in the system. But still, the electrons cannot backscatter. These edges cannot backscatter because the magnetic field has broken the time reversal symmetry. If there's a backscattering that has happened on the other edge, this is forward moving, this edge will be reversible. Backscattered electron need to go to this channel, but this channel is too far because the bulk is insulating, so these electrons cannot backscatter in the quantum Hall regime. That is why if you look at the quantum Hall, it's going to give you a lot more perfect step-like feature, step structure for conductance compared to a quantum point contact. The quantum point contact, the system is small, it's a microscopic system, where quantum Hall effect is a macroscopic system. But still, the condensation comes because of the microscopic edge channels. These edge channels are similar to of the size of the magnetic length, LB, which if you refer back the quantum Hall lecture. There we have defined that. So these edge states are separated by length LB. That is a microscopic length scale. But the system as a whole is macroscopic. But here the system itself is microscopic. So you can still expect some minor scattering from the potential edges or sharp potential coming, teething potential from the gates or impurities around. That can actually contribute backscattering, some amount of backscattering, which is responsible for, some of which is responsible for not having the steps exactly at E square by H as you change the gate voltage. Okay. Because when you change the gate voltage, you are pulling this, you're opening the constriction and you have more and more scattering. But still, the system is in a regime where the transport happens to ballistic, through ballistic, ballistically. But you can still expect some amount of scattering. That is what is causing these steps to be not as perfect as that in the quantum Hall system. That is exactly the reason the quantum Hall effect is used for resistance standardization, not the quantum point contact. Though quantum point contact is much easier to realize compared to quantum Hall effect, which also requires really high magnetic field. But here, the quantization is not as perfect as that of the quantum Hall effect. Okay. And secondly, since even though there are scattering centers inside the sample, in the sample for a quantum Hall system, but the magnetic field, the quantizing field, forbids any kind of backscattering. So the quantization is a lot more stronger, and you really don't require as perfect a sample as that for a QPSC to see the quantization, because the scattering, the backscattering due to the impurities will be taken care by the time reversal asymmetry of the magnetic field. Okay. So these are important conclusions and important points when you look at, one would like to make when you look at these two systems. Both exhibit quantization in transport, quantization conductance or quantization resistance, but they are completely different physics or completely different mechanism. Physics is same, the equations are same, completely different mechanism. In one case you have propagating chiral edge state, in other case you have streamlined flow of electrons through a constriction. All right.